So let me introduce, ladies and gentlemen, welcome again to Asia Pacific Analysis and PD Seminar. Let me introduce today's speaker, Professor Chiun-Chuan Chen from National Taiwan University. He received his PhD in 1991 from National Taiwan University. And after he spent several years in postdoc and academic Sinica, he became faculty member of National Chiun-Chuan University. And then he became a professor of National Taiwan University in 1996. After that, he visited also Harvard University 1 year. And he was awarded the National Chair Professorship in 2008. Okay, his main research interest is, of course, focused on elliptic equation variational problem, but mainly reaction diffusion equation with application to mathematical biology. And today he is going to talk on traveling wave solution for the diffusive Lotka-Volterra system of 3 competing species. Please.
Okay. So thank you, Professor Giga. So good afternoon, everybody. First, I would like to thank the organizers, especially Professor Giga, Professor Goldis, and Professor Howard. So I'm very happy to have this opportunity to give a presentation in this seminar. So here is the outline of my talk. So the main theme of this talk is about the 3 species computing system and a special type of traveling waves. So first, I will consider the method of exact solution and use it to find some such waves. Then I will show you some numerical studies about these waves and some applications of these waves, especially the relation between this wave and the spiral waves. Next, I will use another approach, the so-called growing bifurcation theory, to construct more of these waves. Then finally, I will consider the case when the effect of one species on the other 2 is weak, and under such situations, we can also construct such waves. And then finally, I will give some short conclusion. So the results in this talk are mainly joined with Masayasu Mimura and other collaborators. So I'm very sorry that Professor Mimura passed away in April early this year. I think many of you may know Professor Mimura very well. So I would like to take this opportunity to describe the results joined with or inspired by him and his colleagues. So this photo was taken in Taichung. It is located in the middle part of Taiwan. At that time, we had a conference. Yeah. So as usual, you can see his smile is always very warm and very kind. So now let's turn to our problem. One of the motivations of our study comes from an important issue in ecology, that is biodiversity or coexistence of many species. So here I quote a paper by Milkevich. So in this article, it describes estimate numbers of current species on Earth. So for animals, it is estimated there are 7.8 million species. And for plant species, that is about 300,000. And also, there are many species for fungi. So one can see there are indeed a lot of species on the Earth. So to understand such phenomena, one need to study the biological interaction, such as competition, cooperation, predation, and others. However, in this talk, we focus on competition only. So we are curious about the relation between competition and coexistence. So intuitively, we believe that cooperation can increase the chance of coexistence. So, however, how about competitions? So we can ask the following natural questions. For example, does competition always reduce the chance of coexistence? Or sometimes it can help coexistence? Or we can ask, can species coexist under very strong competition? So these are our central questions. So let me introduce the Lotka-Volterra computing system. So I think most of us learn about this system in the undergraduate course of ODE. So let me show you the two-species system. So here is the ODE. So say we have two species, and the U and the V are the population of these species respectively. And on the right-hand side, we assume that the interaction can be right in these forms. So here we have several coefficients. All of them are positive. So for example, for this C11, it is the intraspecies competition coefficient for U. And this C12 is interspecies competition coefficients. So it means it denotes the effects of U, the effects of V on U. And similarly, the C22 is the intraspecies coefficients, and the C21 is for the interspecies competition. And if we assume that the two species can move randomly, then a typical model is to add Laplacian term into the model. So we also have the PD version. So let's recall some basic fact about the ODE. So there are typically four situations. Two of them are the strong competition case and the weak competition case. So let's see the phase plane. So this is the U-axis, and this is the V-axis. So for the weak competition case, there is only one stable equilibrium for the UVs for this system. So one can show that if you start, say, from this initially, then the trajectory will go to this stable state, F. And you start from here, then similarly, you will go to F. So actually, this F is a global attractor for positive initial data. On the other hand, for the strong competition case, there are two stable equilibrium. So the previous one here now becomes unstable. So if you start from here, then the trajectory will go to the F2, and if you start here, then the trajectory will go to F1. So for F1, only U survives and the V vanishes. For F2, so only V survives. So in any case, either to F2 or to F1, there is only one species survives. So there are very rare situations that say if you start here, then it maybe go to this unstable steady state. That is a very rare situation. So we can say that for strong competitions, only one species survives for almost all initial data. That is for the ODE case. So how about the PD case? So we still interested in the strong competition case. So let's consider this case. So the situation for PD is very complicated. So let me only mention two theorems. So in 1981, Kishimoto proved that if one considers the two-species system with non-boundary condition on a convex domain, then a stable steady state must be a constant. So this is a very beautiful and nice result. So the main idea to prove this is that the two-species computing system is a monotone system. So one can apply the comparison principle. This is a very rough idea. So the implication of this theorem is very strong. So if one would like to consider stable steady state, then this theory tells you on a convex domain, the solution must be a constant. So the situation reduced to the ODE case. So let's go back to the previous slide. So for the ODE case, in strong competition, the only stable steady state are F1 and F2. So our stable solution for the PD must be either F1 or F2. So in either case, only one species can survive. So Kishimoto's theorem implies that on a convex domain, if one would like to consider stable steady state, then only one species can survive. So this is a bad news for coexistence. On the other hand, Matano and Mimura prove that if the domain is far from being convex, say, for example, the domain is like a dumbbell shape with a very thin connection, then there has the possibility to have a stable, spatially inhomogeneous steady state. So this is also very interesting. So how about the general case? The general case is very complicated. So let me just mention one simulation done by Mimura and Toma. So here is the domain. It is a rectangle. And initially, we have one species in the dark region, and the other species survives on the white region. Then after some time, for this case, you can see that the white region becomes larger and larger. Finally, it occupies the whole domain. So the white region indicates that say the second species has a high density in this region, and the dark region indicates the high density area of the first species. So from the final result, you can see that only the second species survive. So this actually is a quite general situation. If you take a domain which is not far from being a convex, then very likely you will see this situation under strong competition. So it seems that it is hard for two species to coexist in general under strong competition. So this is also bad news for coexistence. So therefore, it's nature to consider, say, how about we have more species? So the next question is, of course, to consider the three-species system to see if there are more chance for coexistence. So as I mentioned, that the two-species computing system is a monotone system. So there is a comparison principle. However, for the three-species system, so it is not a monotone, the so-called monotone system. So in general, there is no comparison principle. So that makes the phenomenon of three-species much more complicated. So to study the behavior of the three-species system, so we decide to consider turbulent wave first. So as you know, turbulent waves are important in understand dynamic behavior of a parabolic system. So let's consider the two species case first. So this is a typical profile for the two species systems. So one species is decreasing and the other species is increasing. And the profile remains the same, except it can move to the left or move to the right in a constant speed. So for the two species case, thanks to the results by Gardner and Conley and the subsequent results by Kahn and Fan, we have the following result. So we suppose that the two species are in strong competition. Then up to a translation, there exists a unique monotone turbulent wave connecting the two stable equilibrium. So let me remind what are the two stable equilibrium. So it is actually the F1 and F2 I have shown to you. So the theorem says that there exists a unique monotone traveling wave connecting these two stable steady state. Moreover, this wave is stable. So it's very nice situation. So then we are curious, so what kind of waves can the three-species system have? So first, it is very easy to construct a traveling wave, this profile for the three-species system. So here, the green one, the third species W, is also monotone. So it is not difficult to construct such an example. And in 1997, Miller construct a wave with this profile. And later, Ikeda construct a pulse-like wave. So it is symmetric, but with a complicated profile in the middle. So these two are very nice examples of three-species wave. So if you try to draw other possible profile for the three-species wave, then very likely you will find this profile. So first, you draw the decreasing profile for a species V, then draw the increasing profile for U. So now you have two species. Then where to put the third species? So a natural way is to put the third species in the middle, like this. So one may be curious if there exists such a profile of traveling wave. So actually, there is a natural scenario to consider this kind of traveling wave. So say we assume that V is stronger than W. I use this notation to indicate that intuitively we know that V is stronger than W. And also W is stronger than U, and U is stronger than V. So we have a cyclic situation for these three species. And initially we put V, W, U occupy, we let them occupy the left, the middle, and the right on the real line. Then in the long run, maybe we can expect that the profile of the solution will converge to a Turing wave like this. So this seems natural. So let's call this wave a type 4 wave. So our first question was to consider this problem, the existent problem of type 4 waves. But unfortunately, we do not have good ideas and the method to study this problem. So we decided to turn to use the method of exact solutions. So there were very nice results by Rojigo and Mimura. So they considered the two species reaction diffusion equation. So they developed some method to construct exact solutions. So here is one nice example. So again, we consider the two species computation system. So under suitable scaling, so we can simplify the nonlinear term into this form. So we have many coefficients to be 1. So we have 1 here, 1 here, 1 here, and 1 here. And if one consider a train wave solution with speed s, then the parabolic system is reduced to the ODE system, looks like this. So here is the problem on the real line. So we only have one space variable. And they found that if one assumes suitable assumption on the coefficients like this, then there is a Turing wave solution, UV, which can be represented by hyperbolic tangent like this. So you can see that since hyperbolic tangent is increasing, so U is increasing. And here we have negative sign here, so V is decreasing. So the profile of the train waves is just like the one I showed to you. And the variable here is equals the combination of the original variable x and t. So here s is the wave speed, and the p is some suitable constant, and the p can be determined by this relation. Also, you can see the speed can be decided by this relation. So say if h is greater than 2, then the speed is negative. If h is less than 2, then the speed is positive. So this is a very nice example for the Turing wave solution of two-species system. So then how about the three-species system? So here is the three-species system. So you can see we have more complicated nonlinear terms here. So to apply the method developed by Rojigo and Mimura, so we need to consider the following ansatz. For the two-species case, one important step in their methods is to assume that the second species is a function of the first species. So for our case, we have three species. So we need to assume that v is a function of u, and w is also a function of u, and put these assumptions into the system. So since there are too many equations, so you can see the situation is indeed too complicated. So unfortunately, we failed and could not use this method to find three-space examples. So as I mentioned, since there seems no other better method to deal with the three species, so we decided to use a even more naive idea to find the exact solution. So in a joint work with Professor Mimura, Li Changhao, and Wei Yama, and then later with Thomas, so we use the following idea. So we just assume that the train wave solution is a quadratic polynomial of hypertangent. Then we use very stupid way. We calculate by hand at the beginning. And we were very lucky. We find in example similar to this one. So again, if we consider the train wave solution, then the parabolic system is reduced to an ODE system like this. So we assume that the diffusion coefficients are all 1, are all equals 1. And the wave speed is again is s here. So if we take these numbers to be the coefficients of our system, then we can find a train wave solution which has this form. Again, we have the hyperbolic tangent in the solutions. So you can see for u and v, so v is decreasing and u is increasing. And because of the exponent 2 here, and we have minus sign here, and the hyperbolic tangent only takes values between -1 and 1. So we can see that at infinity, the profile of W tends to 0. So we have a path-like W in the middle. So this is exactly the profile of a type 4 wave. And in this case, the speed is 11/15. So this is an example for the existence of such waves. So this is nice. And actually, you can obtain more examples. So we only need to assume that the coefficient satisfy some suitable algebraic relations. Then we can also construct such type 4 wave. So the next step, we used auto to study the solution structure. So here we consider the bifurcation diagram. So we have C23. So what is C23? So let me go back to the three-speed system. So we fix all of the coefficients in the system except C23. So we use C23 as a parameter. Of course, we can choose other coefficient as a parameter, but at that time we use C23, and this axis is the speed axis. So this is the S. So our exact solution, say, is located at this point. Then use the package auto So we can find that actually there is a branch of numerical Turing wave solutions. Looks like this. So for example, if we fix the value of C23 at this point, say we take C23 to be this point, then we have an exact solution. So the profile of the exact solution looks maybe like this. So this is V, this is U, and we have a small W in the middle. Then for the same C23, there is another Turing wave solution on the branch, which is found by numerical method. So the profile of this wave looks like this. Again, this is V, this is U. And in this case, we have a bigger W. And as I mentioned, for the two species system under strong competition, there is always a Turing waves. So if we consider the situation that the third species is 0, then the situation is reduced to a two species situation. So in that case, we also have a two species wave. So this is V and this is U. So at least we have 3 species. So the two species wave is located around this point. Yeah. So at least we have 3 waves. And one interesting thing is that, so usually the exact wave is not stable, but numerically we know that the second 3-species wave is stable. And the interesting point is that the wave speed of these two are very different. So in this case, actually, for the 2-species wave, the speed is negative, but for this stable wave, the speed is positive. So the third species will change the wave speed dramatically. Yeah, that is a interesting point. So I will come back to this soon. So we found these situations. So okay, so I'm run out of my time. So let me do it a little bit quicker. So as I mentioned, we found the 3-species type 4 wave. So in our second paper, we also found that there is a wave with such kind of profile. So this is say V, and the dot line is V. And for the third species, the profile is like this. So this one is very similar to the one found by Ikeda, but with very sharp peaks for the third species. So we found that this wave appears in more complicated interactions. For example, if we prepare the initial data as follows, so we have this species, the second species, and the third species look like this, then you will see that the profile of the third species becomes this. Then it starts to split into 2 peaks. Then finally, you found the 2 peaks waves. So this is a dynamic behavior related to this wave. So we also are curious that if it's possible to construct exact solution for the two peak waves. So let's go back and take a look the situation about type 4 waves. So in that case, we assume that the wave is a simple polynomial of hyperbolic tangent. And also we notice that the hyperbolic tangent satisfy a simple ODE. So that is the derivative of it equals a simple polynomial of itself. So this is a property of hyperbolic tangent. So however, when we use this ansatz to find the two-peak wave, so we failed. Therefore, we decided to relax the ansatz a little bit. So we assume that the wave is a polynomial of some function, so capital T. So this capital T may be not hyperbolic tangent. Also, this capital T satisfies a simple ODE, so the derivative of it is a simple polynomial of itself. Then we use Mathematica. So since the function capital T is defined implicitly by its own ODE, so we call such a wave a semi-exact solution. So again, we were lucky. So here is our system. So we assume that the diffusion coefficients are equal 1. And assume that the other coefficients satisfy these relations. So here n is a parameter. So the n is a real number which is greater than 3. So under these assumptions, we can find a Turing wave solution, a two-peak Turing wave solution, which can be represented by polynomials of capital T. So the degree of the polynomial is 2 here, 4 here, and 6 for W. And from the representation, actually, we can see that W equals U times V. So this is also interesting. So what is a capital T? So actually, capital T satisfies this ODE. So the degree of the polynomial on the right-hand side is 4. So let me show you the profile of the capital T. So again, this is the equation for capital T. This is our solutions. So when n is very close to 3, the profile of capital T looks like this. So actually, it is very close to hyperbolic tangent. So this is for n equals 10, n equals 20. So you can, in this case, the profile become much more sharper than the first case. And also, the profile for Turing wave has also become sharper and sharper. The height of the peaks become higher and higher. So this is the semi-exact solution. So now let me show you some applications for the type 4 waves. So in the field of reaction diffusion system, people are interested in spiral wave. For example, in the Fitzhugh-Nagumo systems, one can find a lot of examples of spiral wave. So how about the computation system? So the early pioneer work was done by A, Ikota, and Mimura. So they assume that UVW, the equations for UVW are symmetric. So under this situation, they can numerically find the spiral wave. So the next question is, how about if the equations are not symmetric with respect to UVW? So in this case, Mimura and Toma succeeded to construct spiral wave by using the type 4 wave. So the idea is as follows. So this is a domain, and we have 3 species here. So we have the W on the short black line, and the U here, and the V here. So this is the initial data. We look the initial data from the top. So if we look the initial data from the side, then around this part, you will see that we have V on the left, U on the, V on the right, V on the left, and W in the middle. So actually, the profile here, we assume approach to a traveling wave with such a profile. This is a 3-speed type 4 wave. And the profile here will soon approach to a 2-speed traveling wave here. So as I mentioned that we can find numerical waves such that the 3-speed wave have different sign of wave speed from the 2-speed wave. So this is an application of that situation. So with this observation, then you can see that since the wave will go to the left and the wave will go to the right, so there is a rotation mechanism in this wave. So actually, they can find a perfect spiral wave if one prepares the initial data carefully. So again, this W, this U, this V, then finally you can find a perfect spiral wave. Then later in another work with Contento, they can find more new patterns of the 3-speed system. For example, they can find such a dynamic patterns. So this is initial condition, then finally you can see this. And it seems these patterns can survive for a very, very long time, maybe forever. And also they found some new type of traveling wave. They call, so here's one example, they call the wedge shape. So this is a U species and this is a V species, and the dark line is a W species. So the profile will go to this direction. So this black line indicates the trajectory of the tip. So from these examples, we can have some conclusion. So the first one is that it seems 3 species have more chance than 2 species to coexist under strong competition. And it seems coexistence is easier to happen as a dynamic pattern rather than a steady state. So, and also under suitable conditions, even very strong competition alone can support coexistence. And also we find that type 4 waves serve as a basic building block for complicated patterns. So therefore, it is important to construct more type 4 wave, since the previous method of exact solution is too restrictive. So since I'm run out of my time, so let me just very briefly introduce the next approach. So the next approach is the so-called the growing bifurcation theory, developed by Kokopu and the group of Chiun-Chuan and Fiedler. So the idea is as follows. So this is our system. So we take out all of the coefficients and call it tau. So if for some tau, when tau equals some tau naught, if we can find 2 species wave, two species wave for this 3-species system, say we have this 2 species wave, this is V, this is W, and U equals 0. And also we have these waves, this is W, this is U. So for this tau naught, the system has these two species wave with the same speed. So this is the first condition we need to find. Then maybe we can perturb the tau naught a little bit suitably so that these 2 waves can grow and becomes a 3-species wave. So if we write our system into a first order system and draw the picture in the phase plane, then this part like a O1 equilibrium, and this part like O2, and this part like O3. And then at the beginning, we have this 2-speed wave. After shorter propagation, we get a 3-speed wave. So to do this, we need to verify the very complicated condition. So here is a setting proposed by Kokobu. So fortunately, we can simplify the condition a little bit. So first, we assume the speeds are in strong competition. Also, we assume that the two-speed waves are stable as a solution of the 3-speed system. Also, we assume that the linear behavior of the 3-speed system is actually dominated by the 2-speed wave. So then we can show that there exists a lot of the type 4 waves under suitable under these assumptions. So here is one example to apply our solution. So actually we can construct some exact solution. So these are 2-speed wave, this is also a 2-speed wave. Then we perturb the coefficient a little bit and we can find a 3rd-speed wave. And also we has another approach. We assume that the 3rd speed W, the effect of the 3rd species on the first two are small. So we have epsilon 1 here and epsilon 2 here. So under this situation, we can also find the type 4 trailing wave. So this is a joint work with Mimura and Ogawa. And we can find other situation, but use the same setting to find the type 4 wave. So to consider this setting, so if you look at the 3rd equation, then one will find that the combination of U and V here is very important. So if this quantity is large, then there is no chance for W to survive. So therefore, it's very important to estimate this. So in general, we can consider this parallel problem. Say we have UV, and can we estimate the combination of U plus V? So actually, we do not have a good answer. But for train wave solution, we indeed can have an estimate for the combination U and V. So even the diffusion coefficients are different. Yeah. So use this estimate, especially the low bound estimate, we can obtain a necessary condition for the 3-speed problem. That is, so again, here is our coefficient for the nonlinear term. So the theorem says that the growth rate of W must be big enough, at least bigger than this low bound. Otherwise, there is no type 4 waves. So since I'm run out of my time, so I think this is my last result. So let me remind you some conclusion again. So again, we see that type 4 wave serves as a basic building block. And one can use them to numerically construct spiral waves and other patterns. And also, we found that 3 spaces have more chance to coexist. And usually, they coexist as a dynamic pattern rather than a steady state. And so, of course, there is always the following open problem. So can one prove the existence of spiral waves theoretically? So now we have only very few progress on this problem. So I stop here. So thank you very much. I'm sorry I'm out of my time.
Thank you very much for your very nice talk. Are there any questions and comments? Please unmute yourself or raise your hand or chat. Please, are there any questions? Okay, let me start one question. Okay, what do you say, traveling wave is in some sense one dimension. Do you have some traveling wave whose front is curved in a higher dimension?
Yes, but sorry, but not for the competition system. Yeah. So for the competition system, yeah. So we have some trouble in construct train wave for higher dimension.
I see. So what you say is even one dimension, it's very subtle. Yeah.
Yeah, especially for 3 species.
Yeah. Okay.
Yes.
Are there any further questions? Are there any questions and comments?
May I ask about the
Sure,
yes, please.
About coexistence? It seems that if we have a changing environment, then there is much more chance for coexistence even for 2 species. Is it correct?
Yes, it is correct. Actually, once I gave a similar talk, and in the audience there was a person who I think he is a biologist. So he has the same question. He thinks that for the coexistence, other facts like the inhomogeneous environment or the seasoning period on the Earth, they may play more important reasons. They provide more important reason for coexistence. But for our talk, we are curious from the mathematical viewpoint, what is the effect of competition? So if there is only the mechanism of competition, can we still have very complicated patterns of solutions? So from our studies, it seems that the answer is yes. Only the competition itself, if we have the 3 species or more species, then we can produce very complicated phenomena. So I think this is maybe provide one new direction to think about the coexistence. Thank you.
Thank you.
Thank you. Are there any further questions? So if not the case, we we'd like to thank the speaker. And I think there's a coffee time from 3 o'clock. From what time? It's from 4. Your time. It's yeah. But anyhow, within 5 minutes, our coffee time starts. So please, we invite you to join this coffee time to ask further questions. Okay, thank you very much, and we will see you.
Thank you.
In the coffee time.
Okay.
Thank you for your wonderful talk. Please.
Thank you.